Hi there, my name is Lawalu Gofora. I'm a member of the Purdue Quantum Computing Club. Over this summer, members of the club we worked on several projects in teams. My teammate and I, Hadi, we worked on implementing the quantum version of the popular Prisoner Dilemma game, and which we'll be talking about with you in this short video. So what is the Prisoner Dilemma? The Prisoner Dilemma is a zero-sum game that illustrates how difficult it is for two people or players to make decision that is best for both of them rather than being selfish. Take for instance, two robbers were caught by a police officer with no evidence to prosecute either of them, so they have one or two choices while being interrogated. Either they cooperate with each other and do not give any information to the police officer, or they defect against each other and give information to the police officer. So if both of them decide to cooperate, as shown in this chart, and not give any information out, they both get 1 year in prison. If one decides to cooperate while the other defect, the defector takes advantage of the guys that intends to cooperate with him, and he gets 0 year, while the one that decides to cooperate without giving any information to the police officer gets 20 years in prison. And it's symmetrical. And if they both decide to defect, they both get 5 years in prison. So it's obvious here that the best decision for both of them to make is to cooperate with each other and not give any information out. But then here lies the dilemma. Each robber acting in their own interest would weigh their option. If the other robber cooperates, well, the best move is to defect to take advantage of the person. And if the other robber defect as well, the best move is to defect against to protect themselves, therefore defect. So at this point where both players have no motivation to want to change their defect move is known as the Nash equilibrium, despite the fact that reward here is not the optimal reward. So this Nash equilibrium was discovered by John Nash, the popular economist, and what we try to do is to making use of quantum effects such as entanglement and superposition, and building a quantum version of this game to solve this dilemma, which we'll be talking about with you in the other part of this video. Thank you.
Now, in order to develop the quantum version of the game properly, we will need to design the game in such a way that it can be implemented with various quantum instructions and a source of 2 qubits, 1 bit for each player. We'll also have an entanglement factor that will be determined in advance by the 2 players. This factor represents the degree to which the 2 source qubits are entangled together. Now, these 2 qubits that you see here represent the state of the game, and they're initialized to the 0 state, which is shown here as the C vector. So these 2 here in the quantum circuit diagram are the initial state of the game. Next, an entanglement matrix, as described in the paper, needs to be applied onto the 2 source qubits. And that's what you can see with this equation over here. And applying this matrix will entangle the 2 qubits to the degree of the entanglement factor gamma. Afterwards, the 2 players choose their strategies. Each strategy can be represented by a 2x2 unitary matrix defined as a function of theta and phi, where theta is a real number between 0 and pi, and phi is a real number between 0 and pi over 2. We can then define the cooperate strategy by setting both of these variables to 0, and the defect strategy by setting theta to pi and phi to 0. Similarly, we can come up with an infinite number of other strategies that were not possible with the classical implementation of the game by varying phi and theta. One such strategy discovered by the paper was called the quantum strategy. Defined by theta equals 0 and phi equals pi over 2, this quantum strategy has no classical definition and cannot exist in a classical game. This move, however, only has impact when the 2 qubits are entangled by the factor gamma. Each combination of any 2 strategies can be represented by a 2-qubit quantum gate. This gate, a 4x4 matrix, can be created by getting the tensor product of the 2 strategy matrices, which will act on the 2-qubit source. After the 2 players' strategies have been chosen and performed, the 2 qubits need to be unentangled. This can be done by applying the conjugate transpose of the J matrix, the entanglement matrix that we defined earlier, which is defined here as J dagger. Lastly, we can measure the state of the 2 qubits in order to determine the payoff that each play should get. By applying these steps sequentially, we've created a quantum circuit that can be used to play the Quantum Prisoner's Dilemma game. Programmed using the Qiskit and tkinter libraries, we created an implementation of this game that we would like to show you now. So now I'd like to give you all a quick demo of the interface that we created for our Quantum Prisoner's Dilemma game. So let's start by picking our entanglement factor. And just as a reminder, an entanglement factor of 0 means that this will be a classical game. In other words, there will be no special quantum effects or quantum strategies that can be played when there's 0 entanglement. whereas 100% entanglement would be the opposite. So let's keep it at 0 for now and play a classical game. Next, we can choose the strategies for players A and B. So let's say they're both cooperating. And lastly, we can pick the number of rounds that we would like to play for. And I'll just pick 6 as an example. So when we submit the game, you can see that both players in this case get 3 points by cooperating with one another. Now, what would happen if player B chose to defect against the cooperator? Well, what we can see is that player B now gets all the points, and player A gets none of the points. And so this might be incentive for player A to defect against the defector. So now if both players defect, each player gets 1 point each. But as you can see, that wasn't the best that they could have. If they had both just chosen to cooperate with one another, they would have both gotten 3 points. But the problem is that when a player looks at which strategy to choose, they'll notice something interesting about the defection strategy. And that interesting thing is that no matter what your opponent does, as a defector, you will always have an advantage. In other words, you'll always have either more points than them or the same number of points no matter what they do. And just to show this again, let's do defect against cooperate. You get more points. Defect against defect, you get the same number of points. And as a side note, the quantum move in this case has no special impact. Because the entanglement is 0, the quantum move will act as if it is the cooperate strategy. And just for proof, I can, let's say, show you quantum cooperate. It's the same thing as cooperate. Quantum defect, defector will get all the points. And of course, quantum will be 3-3. So now let's say we choose to maximize the entanglement. What would happen now to all these strategies? Well, what we see is that the classical strategies will actually remain the same, no matter what the entanglement factor is. So let's say we do cooperate defect again, defector still gets all the points, defect, it's still 1-1, and cooperate will still be 3-3, which is obviously still the best choice overall. But we can now do the quantum strategy, which has some weird quantum effects. So let's try quantum against cooperate. We can see is that both players will only get 1 point each. How about quantum against defect? Well, now quantum gets all the points over defect. It's no longer like cooperate. Quantum will give the player 5 points and defect will only give 0 points in this case. And how about quantum versus quantum? I have to increase the number of rounds. Quantum versus quantum, both players get 3 points. So now there is a new equilibrium at the quantum move. And that's because no matter what your opponent does, if you're playing the quantum move, you'll always have an advantage. For instance, if you're playing quantum cooperate, you have the same number of points as your opponent. Quantum defect, you have more. Quantum, you have the same. And what happens in this case is that your opponent will go through the same line of thought as you, and you will both end up choosing the quantum move because it is the best strategy for yourself. But what makes this different than the classical game with 0 entanglement is that this equilibrium at the quantum move is the best outcome for both players. Whereas just defecting against one another, let's say you're just both defecting, right? In the classical game, that used to be the best equilibrium, but you're only getting 1 point each. But in the quantum world, where you have maximal entanglement, you can have a brand new equilibrium that gives you both 3 points and is the best strategy for you to play. And this is how the dilemma gets solved. You can try this game out for yourself by going to the GitHub link in the description and downloading all the necessary files and following the instructions in the README. Lastly, we would like to thank the National Defense Education Program and IQ Park for sponsoring our work on this project over the summer. And we of course thank you for watching this video.